All right, hello everybody. Welcome back to another exciting data analysis lecture. We're going to be talking today about multiple linear regression, and multiple linear regression, of course, is the word here multiple is exists to distinguish it from simple linear regression, which is where we just were. So we were talking about simple linear regression. We're going to be extending to multiple linear regression, and we'll notice that we're going to quickly move past the regime that we've been talking about earlier, where we have a bunch of points in two-dimensional space, x and y, and we want to stick a basic line between them. We're going to quickly be able to expand past this pretty simple situation. So for references, we're going to be in Chapter 13 in Truth About Linear Regression and Section 3.2 in Intro to Statistical Learning. All right, so to get us started here, I want to just remind us of where we've been with simple linear regression, right? So in simple linear regression, we have a bunch of points, x and y. Here we've written in random variable form, so we're talking about the relationship between x and y as random variables before we receive observations. And in simple linear regression, we assume that y is related to a single predictor x in a simple form, this intercept plus slope times the single predictor plus some noise term epsilon, where we have some various assumptions that we can make on epsilon. The most basic of which is that it's mean zero, then constant variance and uncorrelated between observations, and then Gaussian with mean zero, fixed variance, and independent between observations. And so we talked about if we have this form and we receive observations, x and y, then we can form the least squares estimator as follows. So our optimal estimate for beta 1 is this beta 1 hat term, which is the sample covariance over the sample variance in x. And the intercept term we estimate with the sample mean in y minus our estimate of the slope times the sample mean in x. So we did this just with some calculus, and this was the lecture where we did not introduce vector notation. So this was 2 lectures ago, and so we had to do 2 different equations, take their derivatives, set them equal to 0, so on and so forth. All right. And so when we wrote that in matrix format in the last lecture, we wrote y is x beta plus epsilon, where we have a random vector x and a vector of coefficients beta. And the idea is that x is a random vector, here a row vector as it's listed, where we have a 1 in one of the columns, in one of the columns, and the x1, for example, in the other. And so the idea is that we can write this expression like this in terms of matrix multiplication, right? And so when we write this, so here I'm just taking the single predictor and putting it, and this is sort of abusing notation a little bit, so bear with me. What's happening is I'm taking the single predictor, I'm putting it in a random vector, which I call x, okay? And the single predictor gets plugged into the second column, and the ones column here gives us this intercept term, right? So when we do this multiplication here, we end up with exactly this expression here. The beta 0 gets multiplied times 1 plus beta 1 x1, okay? So this is writing it as in matrix format, and the point is that we can write this expression here as a dot product between a random vector and a vector of coefficients. Okay. When we wrote it this way, we went ahead and we defined this bold y, which was the y observations. So the y observations, which were y1 through yn, and then we had this design matrix x, which were these x observations, and it was this column of 1s and these column of x's. Okay. So this was x, this bold x here, and this was y. And so when we define these, we showed if we could rederive the least squares estimator in this matrix format as follows, and that was using our vector calculus and we had beta hat, which here again, remember, is a two-dimensional vector. It's a column vector, is x transpose x inverse times x transpose y. Okay? So that's a reminder for simple linear regression. So in multiple linear regression, what happens is we extend past the simple setting. So the simple setting being we only have a single predictor. Okay, so in the multiple linear regression case, we're going to have p predictors, okay, x1 through xp. Each one of them has a slope associated with it. And then we still have this epsilon term, okay? This epsilon term, we have these various assumptions on epsilon. And again, here I'm paraphrasing, okay? I'm paraphrasing these assumptions briefly. Don't forget when I write these tiered assumptions that we have this assumption of uncorrelated among observations and then independent among observations, okay? So that's important, and don't forget that. And so, again, we can rewrite this in matrix format, okay? And when we rewrite it in matrix format, we get the following. And what's happening here is we have a random vector, x, okay, and a vector of coefficients beta, okay? But what we're going to do is basically extend exactly what we've done on the previous slide. We're going to define this random vector as a constant 1, x1, and I'm just going to remove the comma because that's not that typical. X1, x2, so on and so forth, all the way to xp. Okay, I'm going to multiply this row vector times a column vector, which looks like beta 0, beta 1, beta p. Okay. And so what happens is if we do this dot product or this matrix multiplication here, if x is a row vector, what happens is we get beta 0 x1 or beta 0 times 1 plus x1 beta 1 plus x2 beta 2, so on and so forth, and we reproduce this whole thing here, right? And then we add the epsilon on the end. Okay, so well, this is nice because you'll notice that this slide or this expression and the expression on the previous slide, they're the same, right? Just the difference is that we define this random vector x, we just insert a couple of other random variables in it. Okay? And so, just as before, where we define the design matrix and the beta hat vector, so the beta hat vector is what I've just written for the betas, right? It's exactly the same except for everything's got a hat on it. The design matrix, instead of having two columns as it did in the simple linear regression case, what we do is we just extend multiple columns, inserting the additional predictors. Okay? Just a comment here at the bottom, if it's helpful, we're stacking rows. The rows are our observations, right? And the columns are each different predictor, each of the p predictors, and there's p plus 1 columns here because we have the constant column here. Okay, so rows by columns is observations by predictors. Okay. All right, and so just as before, we will set up our mean squared error estimate. Okay, so our mean squared error estimate, recall, is this expression here. Okay, so this expression is, what I'm doing is I'm plugging in x beta, or xb here. So this is the design matrix times some dummy variable b. Okay. And this takes the form of a residual, right? So this is truth minus prediction. Okay. And so this xb here is the design matrix times a vector. What it ends up being is, and we've already broken this down for the simple linear regression case, but I'll write it out once more so we can sort of make sure that we understand it because it's an important bit. But x11, x n1, so this is n observations, okay, and p predictors, x 1p and x np, okay, And so we're multiplying. This is x. What I'm doing here is I'm writing out x b in this matrix multiplication form, and we have this b0, b1, bp. Okay. And again, what we're doing with these b's, as opposed to using betas, so the idea is that beta, these are constants. They represent the true x and y relationship. Beta hat is our estimate, and the b is a dummy variable, which I can just say, take a gradient with respect to some dummy variable. Both of these have definitions, and they're certain values. B is just a dummy variable. So for the mean squared error of some estimate b, right, not the least squares estimator, but some arbitrary estimate, is the following. Okay. And again, you can do this matrix multiplication, and you can see that you should get the predicted value. You should get you get beta 0 plus beta 1 x1 plus so on and so forth, beta p x 1p. All right. So how do we minimize this mean squared error expression? This probably looks a little familiar. This is exactly what we had in the simple linear regression case. How do we minimize the mean squared error? How have we seen it done before? Well, we are going to take some derivatives, right? So we can go ahead and take a gradient, set it equal to 0, so on and so forth, solve it for b, right? But actually, we've seen exactly this expression before, right? So in the simple linear regression setting, it was exactly written like this, right? X and b had a little more dimensions to them, but this was the exact expression that we minimized, subject to x and b, again, being a little bit larger matrices. So matrices / vectors, right? So since this is true, we've seen this before, we've already minimized this expression using our matrix calculus, right? And we actually never used, when we did this minimization, we never used the fact that we were only working with 2 predictors. We actually did this generally. And so you can convince yourself, I hope this is convincing enough, but you can flip back through the slides where we did this derivation in the simple linear regression and matrix format lecture. Convince yourself that we never had to use the fact that we only had 2 predictors. That minimization was just for arbitrary matrices x and b, matrix and vector x and b. Okay? So it follows that the same minimization expression holds, right? So the minimizer is this thing. Okay? So this is the benefit of using the matrix format. I talked about how the matrix format is going to generalize and be better for us in that sense. And this, the benefit of using this matrix format for simple linear regression is when we introduce multiple predictors, we actually don't have to do anything else because the notation works exactly the same. The derivation works exactly the same. Okay, so this least squares estimator still holds even when x. So remember in the simple linear regression case, x is n observations by 2 columns, and in the multiple linear regression case, x is n observations by p plus 1 columns. There's the p predictors plus the one intercept term. Okay, but actually this derivation does not rely on the shape of x, right? We did it arbitrary using the matrix calculus. So that's great because we can just reuse that simple or that least squares estimator in the multiple linear regression case. Okay, so that's what's the same about simple linear regression and multiple linear regression. But what's different, right? Obviously, as we proceed into higher dimensions, not everything is going to be the same. And in particular, graphics are much more difficult in higher dimensions, right? It's very easy for me to just say, all right, right, we have a bunch of points, x and y, they do a thing. You know, the illustrating of the examples is extremely easy in 2D. And once we have multiple predictors, you know, I can draw something 3-dimensional if I have 2 predictors. And once I have more than 2 predictors, I'm just out of luck. It's very difficult to graph. We're going to have some techniques for doing so, but this is just a drawback, right? So it's harder to visualize what's happening. Okay. The other thing is that instead of the conditional expectation for some fixed quantities of these predictors. So in the simple linear regression case, right, we didn't have any of this bit. We just had a single predictor, and as we moved this x1 value, this lowercase x1 value, we had a line. So that is the conditional mean of y given x. As we move this x around, this conditional mean traced out a line, right? And as we introduce more predictors here, and we slide all of them around, x1 through x2 through xp, this conditional mean draws out a plane instead of a line, right? I'll show some pictures later on, which sort of will confirm that for you. But what you can imagine is, as x1 increases, right? As x1 increases, we see a line. As x1 increases for some fixed values of these other predictors, we have a line, and vice versa. If we fix x1, only change x2, we also have a line. And as we can move them arbitrarily, we have a plane or a hyperplane in higher dimensions. Okay, so we're going to recall the data set that we've been working with for the past couple lectures. This is the voting data set in 2016. This relates internet search traffic for various sports to how different communities voted in the 2016 election. And so what we're going to do is revisit that, and instead of using simple linear regression, we're going to use a multiple linear regression model. Okay, and so in order to do principal data analysis, we will start with an exploratory data analysis. Sort of as we outlined in the first homework, we should understand the data before we start doing modeling, and this is just basic plots, histograms, so on and so forth. So we'll start with an EDA before we get into the modeling. Okay, so first thing here is a correlation plot. The correlation plot, this is plotting correlation values, a correlation matrix, right? So we've talked about what a correlation matrix is. A correlation matrix is a matrix that holds pairwise correlation in it. And so what's happening here is we have along the diagonal, so a correlation matrix, right? This value here has the correlation between NFL viewing and NFL viewing. Correlation between a variable with itself is 1. So along the diagonal here, we have all of the correlation of a variable with itself. On the off diagonal, we have the correlation of NFL with NBA, NFL with MLB, so on and so forth. And this plot is presenting all of the correlations to us succinctly. And so we see here, according to the scale, the correlation between viewing the percentage of search traffic related to NFL and the percentage of search traffic related to NBA is slightly negative, maybe, I don't know, 0.2 or some, a negative 0.2 here, okay? And so NFL search traffic and NBA search traffic are negatively correlated. What we're looking for here as we look through this is just what variables are trending together, right? And so in particular, any variable that has high correlation with this variable we wanted to predict, the percentage of the community voting for Donald Trump in 2016 is something that's especially important to us for the sake of prediction, right? So we see this correlation matches what we saw in the scatter plot. So we saw in the scatter plot that it looked like NASCAR had a strong positive relationship with the vote prediction that we wanted, the vote response that we wanted to predict, and so we see here maybe correlation of 0.5 or something like this, right? So when I'm interpreting this, I'm looking for large values in general. I want to say, okay, so NBA has a larger relative to a lot of the other dots in this plot, has a negative relationship with the quantity we want to predict. And so it might be a useful predictor, the fact that as communities have more search traffic related to NBA, the percentage of folks voting for Donald Trump goes down. Okay, so even if the relationship is negative, it can still be useful as a predictor. The other thing that I want to mention here is this: we'll come back to this later, but there's something intuitive here that if that let's say that the communities which watched a lot of Major League Baseball were the exact same communities that watched a lot of NBA. Okay, and so what would happen there is if we tried to include both of these as predictors in a model, we would have redundant information, right? There's sort of the idea that I can only use if I had this information and you gave me a carbon copy in another variable, that it wouldn't be useful in a model, right? So we might be able to assess that from the correlation matrix, right? We don't particularly have that. We see that we don't have a large blue value where one value is a carbon copy of the other. But that's something we might be able to assess here is, okay, I would say, maybe this variable is useful, this NASCAR variable looks like it's going to be useful as a predictor, and then I'll go through and say, are there any other variables which look like they're providing me the same information as NASCAR, i.e. they're highly correlated with NASCAR, because that might be providing me some redundant information. Well, we're going to be talking a lot more about this in future lectures, this idea of redundant information in predictors, but I just want to highlight what I'm looking for here in this correlation plot. So the other thing I'm going to do here is create what's called a pairs plot. So this pairs plot is showing me pairwise scatter plots. Essentially, it's similar to this previous example where we have this correlation plot. It's just each of the entries in the matrix are now scatter plots instead of correlations. So I have NFL on the y-axis plotted against NASCAR on the x-axis, and I can quickly assess a lot of scatter plots. Okay, so I see here if Trump vote is my y-axis, okay, and I'm looking along the x-axis, I see that as the x-axis increases, the y-axis also increases here in this scatter plot. We've seen this scatter plot before. I can see maybe a slight negative trend with MLB, maybe more pronounced negative trend with NBA search traffic, and NFL to me looks like a pretty big wash, maybe slightly positive. All right, and again, I can assess, how are different variables trending together. We see, for example, this one's kind of interesting. This is showing that as the percentage of search traffic related to NASCAR goes up, the percentage of search traffic related to NBA goes down. Okay, so this is sort of suggesting that communities which watch a lot of basketball are not the communities which are watching a lot of NASCAR. Okay, so there's a negative relationship between the two of them, and that emerges here. Another pairs plot. This is a fancier pairs plot where I simultaneously have correlation information, density plots in the form of kernel densities along the diagonal, and scatter plots over here in the bottom triangle of that matrix. Okay, so lots of different ways to view this information, but the point is we see what I expect here is that NBA seems to be the second most useful predictor after NASCAR. Okay, now I can assess that from this pairs plot. The relationship just seems more pronounced. Okay, so new R commands. So in R, we can build a multiple linear regression model as opposed to a simple linear regression model using this LM function just as before, but instead of just introducing a single predictor, x1, we will introduce multiple predictors, x1 through xp, just in the same way we've done where we can just do plus, so on and so forth. This is how we build multiple linear regression models. And so, let's jump into R for a little bit. Okay, let me blow this up so y'all can see it better. Okay, so here's the data that I've been referencing. This is the package that the data comes from. This is the package that the correlation plot comes from, and this is for the fancy pairs plot where I had this simultaneous presentation of correlation, density information, and scatter plots. Okay, load up the data. grab the columns we use, select the used columns. This is all pretty routine. And then I'm going to change this Trump 2016 vote. I'm just going to abbreviate it to Trump vote in terms of the column name, only because just burdensome to write it out every time. Okay, so how to make the correlation plot. So this is just part of the exploratory data analysis. I'll go through this really quickly for the sake of being thorough. This is the correlation plot, which we saw earlier. So I'm running core plot on the correlation matrix. Here's the pairs plot that we saw earlier. Okay, and then here's the fancy pairs plot. It's even got a fancy loading bar. And we can see scatter plot, density information, correlation on the upper triangle here. Okay. So what I'm going to do next is I'm going to build some simple and some multiple linear regression models. I'm going to compare them. Okay. So this is me setting my seed. What this does is it makes the train test split reproducible. Okay. So this is actually important, and what's happening here is I'm going to randomly split the data into a training set and testing set, but if I go back and I run this again, I want to have the same training set and testing set. So when I set this seed, it makes the randomness reproducible in the sense that the random vector, I'll get the same random vector, or a random split rather, if I set the seed. Okay, so you can set it to 0, set it to 1, those are pretty common. So I'll set the seed, get my train indices. So here I'm sampling 80% of the rows to get my training indices, selecting a training set, and then everything else is going into the testing set. Okay. So then I'm going to build a simple linear regression model. So this is simple linear regression predicting the y variable from just a single predictor. And here I'm going to build a multiple linear regression model where I'm predicting the y variable from the NASCAR variable and also the MBA variable, right? This is the second predictor, which I may identified as potentially important, with this one having a negative relationship. Okay. So then let's go ahead and plot here. I'm going to plot my simple linear regression model as we've done before. So here's the plot. And then here's the simple linear model predicting y from x. Okay. So how do I extend this to multiple linear regression? Well, to do this, I'm going to have to plot a plane instead of a line. Okay. And so I'm going to load up this scatterplot 3D package. This is how we can make a plane in R. It's not necessary to do this every time. I just want to show the analogous plot as a simple linear regression plot with two predictors. Okay, so here I'm plotting x and y, that is NASCAR and MBA, against z, which we'd be predicting, and here's a scatter plot of x, y, and z. Okay, and here is a plane. This is a plane which determines my multiple linear regression model. Okay, so here what we see is as NASCAR percentage goes up, we see that it looks like the percentage of votes in the various communities goes up for Donald Trump, and it's a little hard to see, and this is the downside of having these three-dimensional plots. It's a little hard to see what's going on with the MBA axis, right? So yeah, let's see. Yeah, and so probably the easiest way to look at this would be to say, what are the coefficients of the multiple linear regression model? Right. So here's my plot. This is basically the high-dimensional generalization of the plot we just saw. But what I can also do is go in here and say, what are the coefficients of the multiple linear regression model? Okay. So here I see intercept 52. NASCAR has this is the slope of the NASCAR predictor and the slope of the NBA predictor. So here we see as NBA increases, right, the expected y value will decrease because this coefficient is negative. So this allows us to just clarify what we see. Oh yeah, indeed, as this variable increases, this is decreasing, even though the perspective makes it a little hard to see there. All right. So let's see. So another thing that we can do here is just to compare the models. Okay. So here I have a function which I've written. You may or may not have seen R functions before, but what this does is this just writes a bunch of code and condenses it so I can reuse it again to compute the training and testing error. That is the training and testing mean squared error for a model. So I give this function a model, that is a multiple linear regression model, a simple linear regression model, whatever I have, and what it's going to do is it's going to find the training mean squared error by taking the mean of the squared residuals, and then it's going to find the testing mean squared error. I can't just extract the training residuals from the model. I have to compute the testing residuals. So this is y minus predicted y, okay, where I'm putting the testing data in there. And then I square those residuals, take the mean of them, and I'm returning a little bit of a little data frame which has the training mean squared error and the testing mean squared error. Okay, so let's just execute this really quick. And then I'm going to compare the simple linear regression model's training and testing error to the multiple linear regression model's training and testing error. Okay, and so what I see is, well, let's look at this. So the training mean squared error, okay, so this is simple linear regression, and the testing, simple linear regression, I'm going to compare training errors. We see that the training mean squared error goes down as we add this additional predictor, right? Training goes down, but testing goes up. And remember, training we should prioritize testing mean squared error over training mean squared error. So this is just a little bit of increase, but it is an increase. Okay, so what this means is on a fresh snapshot of data, I've done worse with the multiple linear regression model, including the new predictor, than just using the one predictor, the NASCAR predictor. Okay, so what this tells me is just based on this information, I would not prefer a model which has the MBA predictor. Even though it brought down my training mean squared error, the goal is to generalize, and we have not generalized as well. Okay. Another thing I could do, I can add even more predictors. So here's a second multiple linear regression model where I'm using NFL as an additional predictor, right? The percentage of search traffic related to the National Football League. Okay. Again, I will look at the training and testing errors, and right, you can see now the benefit of using this function is I can just feed it whatever model I want, and it'll compute the training and testing error. So I see again the training error has gone down, but the testing error is going up. Okay, and so this is the trend. The idea here is I suspect that we might have a little bit of overtraining going on. The training mean squared error is going down, but the testing mean squared error is going up as I'm adding more predictors. So I'm generalized even worse when I add the NFL predictor to the NBA and the NASCAR predictors as I was just having the NASCAR and NBA predictors. Okay. Another example, I can use a simple linear regression model just using NBA instead of NASCAR, right? And here we have the mean squared error has gone way, way up. Again, testing being the most important, the more important of the two over training and testing, and it's gone up. So this simple linear regression model seems to win in this comparison. Okay. All right. So great. That's what I have to say. That's what I have to say about how to do multiple linear regression in R. Let's jump back to the slides. And so the next thing we're going to talk about is actually a little bit more theoretical. So we've talked about how to implement multiple linear regression model in R, and we're going to talk about next this what's called the truth plus error representation. Okay, so the truth plus error representation, it's on the theoretical side, right? So we talked about sort of the goals of this course, the three different types of problems we're going to be working on: theoretical, simulation, and just hands-on data analysis. This is understanding multiple linear regression more from the theory side. So if I fix a design matrix X, okay, so that I have fixed X, I let Y vary randomly according to the epsilon term, right? So I fixed X, epsilon is a random variable, therefore Y is a random variable where it only depends on the randomness in epsilon, okay? Then, as we know, beta hat is the following, right? This is our expression for beta hat, X transpose X inverse, X transpose Y. But here I'm letting beta be random, okay? So the idea is I have a bunch of X, there's some Y's associated with them which I haven't realized, okay? And how does, on beta hat, right, is then depends on what we get for Y. So the least squares estimator here is random depending on the noise in epsilon, which is lending its randomness to Y, okay? And so if this is true, right? So if beta hat is this this expression where this is Y, well, we know what Y is if Y satisfies our this linear model assumption, right? Then we can go ahead and just plug in what Y is, right? So here I'm reducing beta hat and just plugging in what I know to be Y, and then look what I get here. I get X transpose X inverse X transpose X times X transpose X inverse X transpose epsilon, right? Or excuse me, plus here. I misspoke, but you get the point. So you distribute this matrix on the outside to both of these terms. What happens is you get an X transpose X and X transpose X inverse on the one on the left. So you just get beta, and then you get the X transpose X, X transpose epsilon on the right. Okay? So this is what's called a truth plus error representation. And where does this truth plus error representation name come from? So what we're doing is we're representing beta hat, our estimate, as the truth, beta, plus some error, right? So this is, again, for fixed X, the epsilon is the only quantity that's varying. This is our randomness, but this is estimate, truth, plus error. Okay? This is going to be extremely useful for us because this simplified form makes computing some properties of beta hat very easy. Okay? So the first question I'll ask is, what is the expectation of beta hat? Okay? So how can we compute the expectation of beta hat? Well, as I suggested, the truth plus error representation is going to come in handy for us. So the truth plus error representation, I've written it on the top equation here. Okay. And, well, if I want to take the expectation of beta hat, I can just apply expectation to both sides. What do we know about the expectation across this sum? Well, I can apply the expectation to each piece, right? When I apply the expectation to each piece, this bit is constant. This is just some fixed true value of beta. This bit is random, depending on epsilon, right? And then, but this is fixed, right? I said fixed X, varying epsilon, therefore varying Y. We can pull out the matrices out of this expectation, and I'll just apply it to the epsilon. And what is the expectation of epsilon? Well, under our first assumption, so this is our most basic assumption, right? That is we have that epsilon is mean 0 for all x, right? So as long as the most basic assumption holds, that is for each fixed value of x, the expectation of epsilon is 0, then this whole thing becomes 0, and the expected value of beta hat is beta. Okay. So what this is saying is that the expected value of the estimate is equal to what we intend to estimate. that is the true value. And this is the definition, if you recall from the miscellaneous facts lecture, this is the definition of unbiased. So this we conclude, and through the truth plus error representation, we are able to show that beta hat is unbiased. Okay? So just some properties of expectations combined with the truth plus error representation. All right? So what about, once we have the expected value, another thing that we might want to compute is variance, right? This is our two sort of standard quantities that we've been using, expectations and variances. So what about the variance of the least squares estimator beta hat? Well, so assume that the variance of epsilon is sigma squared, okay? So here, we have that epsilon, in this notation, epsilon is a random vector of epsilons for a bunch of different observations, right? So it's just a random sample of epsilons, and so it's actually a covariance matrix and not just a single value. So we're assuming that the variance of epsilon is constant, right? That is, the variance is some sigma squared value, and it does not depend on the observation, okay? So this is basically a constant variance assumption, okay? But also, because the off-diagonal terms are 0, this is constant variance, and the epsilons are uncorrelated across observations, i.e., this is our second assumption. All right. So if we assume this, if we have the second assumption, we can actually compute the variance of the least squares estimator. Okay, here the variance, of course, means the variance covariance matrix, because this is a vector. So using the truth plus error, we'll take the variance of this. Okay, here we're adding a constant, so something which we're computing the variance of. Recall that from the miscellaneous facts lecture, adding a constant to a computation of a variance doesn't do anything for us. We can just drop it. So I've dropped the constant term here. Now I have the variance of some constant matrices times some random quantity. And what happens here when we compute this variance? Well, according to the rules, we pull out the matrix, put it in front, and pull out the matrix and put its transpose in the back. Okay, so that is what I've done here. Pulled out in the front, pulled out, transpose in the back. Okay. Well, now we know what variance of epsilon is. It is sigma squared times the identity, right? So because sigma squared is a scalar, I'll just put it out front and combine all these pieces together, okay? Here I am taking the transpose of this expression. Now how do I take the transpose of this expression? Well, remember, we flip the order and apply the transpose to each one, right? So I have x transpose x inverse, x transpose, and then flip the order. This becomes an x double transpose, which is just an x, and then x transpose x inverse, I take its transpose, and this follows because, and this is something I mentioned in the previous lecture, the inverse of a symmetric matrix is indeed symmetric. Okay, so we've shown that x transpose x is symmetric, therefore x transpose x inverse is symmetric when that inverse exists. Okay, so it's its own transpose, we get the following, and then what happens here? Well, we have an x transpose x, we have an x transpose x inverse, and we're left with sigma squared x transpose x inverse. Okay, so lots of algebra, but what's happening is we're computing the variance of the least squares estimator. So this is the variance covariance matrix of this vector of coefficients. Okay, and if the variance of the noise term is fixed at some value sigma squared, then we can compute the variance of the least squares estimator, and it is indeed this quantity, this variance covariance matrix. Okay, so we've computed the expectation of the least squares estimator and the variance of the least squares estimator. Okay, so for example, right, if you wanted to find, right, the variance of, the variance of beta 0 hat, right, that is the variance of the intercept term. Well, this is a variance covariance matrix. It's the first one in this vector, and so to find its variance, it's right, the variance of beta hat 0 is the covariance of it with itself. it is the first term along the diagonal of this matrix. Okay? So yeah, and we can find pairwise covariances also in this matrix. Okay, lastly, so you notice a trend here where we have these tiered assumptions. So there was the first assumption, which was the expectation of epsilon is 0. That gave us unbiased. The second assumption, which is the constant variance of epsilon and uncorrelated across observations, that gave us we could compute the variance of the least squares estimator. Lastly, we can find the distribution of the least squares estimator with the third assumption. Okay. This is epsilon, so the epsilon vectors are normal, mean 0, constant variance. Okay, here again, because they're uncorrelated and they're normal, they're independent. So this is our third assumption. Okay, that is the what's called the we sometimes call the Gaussian errors assumption. Epsilons are Gaussian. Why? So, well, we know that beta hat has mean. So mean beta, variance covariance matrix given by this. This is the last. So this is the last two slides, right? But the fact that it's actually Gaussian itself comes from a certain property, which we've seen a few times, which is the fact that linear transformations of Gaussian random variables are in fact Gaussian, right? So why is that? Let me jump back here. So beta hat is a constant plus some constant linear transformation. This is constant, again, for fixed x. And if epsilon is Gaussian, right, so this is beta hat is a linear transformation of Gaussians, right? So this is what allows us to conclude that beta hat is indeed Gaussian. So we know its mean, we know its variance, covariance matrix. It's Gaussian because it's a linear combination of Gaussian epsilons. We can actually establish similar properties for the residual vector. So again, for fixed x, epsilon treated as that random variable, we can have a residual vector, which is true minus estimate. Okay, this true y is x beta plus epsilon, and the estimated is x beta hat. Right? So I'm just plugging in y and y hat here, and then I can pool the x's here. I can substitute in the truth plus error representation. So here we're getting a lot out of the truth plus error representation. We can get even more. So x beta. Okay, so this is just tagging along here. I've moved the epsilon to the back, so I can work with these two expressions right next to each other. I have x. This one's just coming down, and then for beta hat, I'm plugging in the truth plus error representation. Okay. Here I have x beta minus x beta. That just becomes 0. And here I distribute the x to this side here. I get negative x transpose x inverse, x transpose epsilon. Okay. Plus this epsilon here, which is just tagging along. And so, have we seen this matrix before? Indeed, we have. You may have to flip through some old slides to remind yourself, but this is the hat matrix. Remember, a hat matrix is the matrix for which y hat equals hy, and it was defined as this matrix. Okay, this is the hat matrix, and so what we have is that we've just written the residual vector as the identity matrix minus the hat matrix times the epsilon vector. Okay, so this is epsilon. This is residual vector equals some linear combination of the epsilons. Okay. So why is that important? Well, from this expression, I'm not going to do it in detail, but you can. Some of it is in your homework. You can actually derive properties of the residual vector. So for example, if you had to show that the residual vector was unbiased, right, or mean zero, expectation 0. So the expectation of this residual vector was 0. How could you do it? Well, you could use what we just derived here. You could say the expectation of the residual vector is the expectation of this. Pull out all the chump change in the front here. You're left with the expectation of epsilon. The expectation of epsilon is 0, so on and so forth. So you can do exactly as we've done for the least squares estimator for the residual vector. Okay. There is a fact here which we're going to use and which I'm going to have you show in your homework, and it's that if H is an orthogonal projection, okay, we defined this in the last lecture. That means that a matrix which is an orthogonal projection is one which is idempotent. When you square it, it equals itself, and symmetric. When you transpose it, it equals itself. Then so is the identity matrix minus that matrix. Okay, so if H has these properties, then I minus H has these properties. Okay. So what we can show here is if epsilon is mean 0, then the residual vector is mean 0. That's just applying the expectation to both sides, as I was suggesting. We can show that if epsilon is constant variance, this epsilon vector has this variance structure as before, where it's sigma squared times the identity matrix. We can take its variance, right? Taking the variance of a linear combination. We pull one of these matrices out, we pull another one out and put it in the back and transpose it, right? According to that variance rule for working with random vectors. This variance term here, sigma squared times the identity, we can pull out the sigma squared, the scalar. This is some properties. If I minus H is an orthogonal projection matrix, then it's symmetric, so its transpose is equal to itself. And when you square it, it's equal to itself. So that allows us to reduce this right-hand side to sigma squared times I minus H. Lastly, if epsilon is normal, the residual vector is normal. Why is that? The residual vector is a linear combination, so for some constant matrix here, times a Gaussian vector. So we have a linear combination of Gaussians, therefore we have a multivariate Gaussian in the residual vector. All right? So this is actually important because what we have is a bunch of properties. We're going to be able to verify modeling assumptions. Okay, these modeling assumptions are these 3 tiered assumptions. Epsilon, or the expectation of epsilon is 0 for every x. Epsilons are constant variance uncorrelated, and the third one being Gaussian distributed, mean 0, constant variance epsilon. By looking at the properties of the residuals, so we're going to be able to verify these assumptions by looking at the residuals, and we know that if epsilon is mean 0, then the residual vector will have mean 0, right? This is what we just talked through. Okay. We know that if epsilon has constant variance, then the residual vector will have constant variance, where the variance is determined by this quantity here. Okay. Lastly, if epsilon is normally distributed, okay, then the residual vector will be normally distributed. And this is this last property we talked about, linear combination of Gaussians is Gaussian. Okay, so what happens if I look, you come to me and you say, hey, I have a linear model, here's your residual vector, I look at it, and I just do not believe that it's a sample from a vector which has mean 0, right? Well, if this doesn't hold, then we know that the original assumption didn't hold, because if it did, then we would have had to have that conclusion mean 0, right? Likewise, if the residual vectors do not have constant variance, the residuals do not have constant variance, then epsilon doesn't have constant variance. And if the residuals do not look normally distributed, then epsilon was not normally distributed. Okay, so basically what we're going to be able to use is these residuals to look back and basically call BS on the original assumptions, mean 0, constant variance, uncorrelated, and normally distributed independent. All right. So here's an example. Okay, so here's some data. I have x, y. So this is just 2 dimensions, single predictor, and we have a nonlinear relationship between x and y. That's okay, but I just want to look at what some residuals might look like to see how we can use our residuals to assess assumptions. Okay, So here's a model. Here's one model. This is predicting y from x using the conditional mean of y given x is this red line. Okay. And so what happens? So now I'm going to look at the residuals. Okay. So remember the residuals are the true points, the black points, minus the corresponding red points. And so here's my residuals. Okay. So what I want to do to assess mean zero constant variance, so I want to see, is it reasonable that this sample, right, for each x, that we have mean zero or near mean zero, right? So that is, as you change x, that all of these points have approximately mean zero. For me, I'm not too unhappy with that, right? That claim. They seem to be sort of centered around a line at zero. Okay. Another thing I could look at, I would say, is this constant? Are these constant variance? As I vary x, do I see the variance changing? Right? I might say, well, so this variance looks kind of, the spread of points here looks kind of large, right? Here. And looks kind of small here. So that might make me say, well, maybe the variance is not constant. But remember, there's a lot more points here than here, right? So if we only have a few points, it's harder to see what the spread of the data is, what the variance would be. So for me, I don't see any trend where something that would really be a red flag is I have sort of similar amount of points to this, but they're either way spread out or they're really clustered together. This would make me think that the variance is changing. But for me, I don't have any evidence from this plot that the variance is not constant as we change x. Okay, so the variance of the residuals is not constant as we change x. So assumption 2, I'm generally okay with based on this plot. And then the third one is assessing for are these residuals Gaussian? And to do so, we're going to look at specific plots, plot these on a histogram, look at QQ plots, which we'll talk about momentarily. So returning to the data again, here's another example of a model I could use. So here's a simple linear model where I'm just using increase x. I'm fitting the slope and the intercept here. So we can see, because this model is not a good fit for the points, we have sort of a disaster. And I'm going to look at the residuals here. So the residuals, again, are these black points minus these red points, the corresponding red points. Here's the residuals. Okay, this looks very similar to the original plot, but the y-axis is changing. This is the true y minus the predicted y for each value. Okay, and so we see from this residual plot, it's not mean zero, right? So as we change x, the mean of the residuals looks negative, 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 positive, positive. The mean is not zero for all x, right? So this blows the first assumption that epsilon should be mean zero for each x out of the water, because if that was true, we would see epsilon that the residuals were mean zero, and we see distinct evidence here that the residuals are not mean zero for all x. Okay, so for this model, right, we see evidence that the epsilon tends to be negative, epsilon tends to be positive, and epsilon tends to be negative again, i.e. it's not mean zero for all x. Okay, kind of a pronounced example, but one I just wanted to include to emphasize how we can use the residuals to assess the modeling assumptions. So let's go back to the example, the running example we've had where we were using percentage of search traffic for different sports to predict percentage of votes for Donald Trump in 2016. We see here our simple linear regression model. So let's look at the residuals and let's assess how the health of the modeling assumptions, basically. Another word for assessing these the assumptions via these residuals is called diagnostics. So we're going to do diagnostics, and the idea is sort of we're doing a health check of the assumptions by looking at the residuals. So here's our residuals. So that is, I've subtracted the true minus the predicted. Now I'm looking for mean zero. Okay. Well, in this region here, I see evidence that the mean is not zero. That is, every single one of these points for search percentage, traffic, percentage of search traffic related to NASCAR, for all of these communities where we have low values of search traffic, I appear to be, remember this is truth minus predicted. So the fact that this value is, these residuals are negative, right? So this is truth minus predicted. For it to be negative, what it means is that y hat, the predicted value, is greater than y. So I'm overestimating the quantity of interest here. Okay. So here my prediction is too high. That makes sense. Well, here in this region, I am too high. Right? I'm overestimating these values in this region. Okay. So here we have some evidence that epsilon is not mean zero, because we see that the mean is distinctly negative here. The mean appears to go up a little bit. Perhaps in this region the mean is greater than zero. It's hard to see. This one is certainly more defined here. As we go up into these other regions, I'm not too unhappy with this assumption, right? So for this region, I'm sort of sketching a line through here to say, is it reasonable that the mean of these points would be 0 as I vary x? Yeah, reasonably so, right? I'm not too unhappy. But here, I see evidence that there's a lot of points which are less than 0, too many that I would expect if the mean was actually 0. Okay. So here we see the assumption 1 may have some flaws. If we look back at the multiple linear regression model, again, we want the mean to be 0 for all values of x, right? But in the multiple linear regression model, we have 2 variables for x, right? So instead of just varying 1, it can be variable x, variable NASCAR percentage, and variable NBA percentage. Okay, so here's the residuals. Again, this is truth minus the predicted. So what I'm doing is I'm taking for each point, I'm taking the true z value, the true value on the z-axis, minus the predicted value on the z-axis. That is the point on the plane. I get the following, okay? And the idea here is that I'm looking for, is this cloud of points mean 0 for every x? So I'm looking for something sufficiently blobby centered around 0. That is, as I change x and I change y, it should be reasonable that this is all mean 0. Again, it's hard because this is a 3-dimensional plot. This is one of the drawbacks that I was talking about going to multiple linear regression. But instead, we'll look at them actually. We can look at snapshots. So we can actually look at just plotting the residuals against one predictor and the residuals against another predictor as one way to assess. So here is plotting the residual against one of the predictors. Okay. So again, we see distinct evidence that the mean is below 0 here. So this is not the simple linear regression model. This is a different model, but we see we're having the same problem. When we plot the residuals against the NBA percentage, here we see, I don't see anything in this plot that is especially problematic. It's reasonable for me to believe that for each fixed x, the points I'm receiving here are mean 0 or near mean 0. But because I've broken the assumption for one of my plots, I can stop there. I can say, so I have evidence from this plot that the first assumption does not hold. I don't need to check the other plot to make sure that it breaks there as well. I have sort of forbidden structure in one of the plots that makes me say I would call BS on that assumption that the epsilons are mean 0, because if it was mean 0, we've seen through some of this theory that we've derived that the residual vector should be mean 0, and I see evidence that it's not. Okay. A third residual plot, this is actually going to be very important to us in the context of multiple linear regression. So a third residual plot here is I'm plotting the residual against the predicted value. Okay, and we haven't talked about this one in as much detail, but we should see similar structure here in that we should see that the residual should be mean 0 as y hat is changing. Okay, so this is as y hat is changing, we should see that the residual is approximately mean 0, approximately constant variance, right? Again, in this region here, for low predicted values, I see some evidence that the mean is not 0. I have a lot of points which are less than 0, 2 points which are greater than 0. I'm detecting some forbidden structure. Okay, this is the predicted value y hat. All right. And the reason that this is actually one of the reasons this is important in multiple linear regression is that the predicted value is easy to plot against, right? Y hat. No matter how many predictors you have, y hat is just one variable. So I can always plot y minus y hat against y hat. And again here, I'm looking for forbidden structure. I'm saying, are we mean 0? Are these points approximately constant variance? Are these points approximately Gaussian? Okay? And this allows me to assess the health of those 3 assumptions. So big takeaways, we can use residuals to assess model fit, right? We've derived some theory. We've shown that if epsilon satisfies various assumptions, right? Some various modeling assumptions, as we've called them, mean 0, constant variance uncorrelated, Gaussian distributed, independent, that structure from epsilon will percolate down into the residuals. And by looking at the residuals, we can say, we can detect forbidden structure in the residuals, which makes us refute the assumptions in epsilon. Okay? And so you can use it along with your test mean squared error to compare models. Okay? We're going to progress along in this direction, but having these various assumptions on epsilon is going to allow us to say more about, particularly on the inference side, about the fit of our model. And so we can say, for this model, I see we have mean 0 assumption. For this other model, I have a mean 0 constant variance assumption. At least I haven't negated it with the residuals, so I'd be willing to say that it holds. And this is another way of assessing model fit, which can be used alongside test mean squared error. So we've been using test mean squared error to compare models so far. The health of the various modeling assumptions is another point of comparison between models. So I'm going to take a break here and come back. But what we're going to talk about in part 2 of this lecture is what to do about it. So that is, let's say we have bad residuals, right? We know that we've looked at the residuals. They're not working for us. They're saying that our modeling assumptions are breaking. How can we go about and fix it from a modeling perspective? Is there any way we can salvage some of those different assumptions? So that's what we're going to do in the second part of the lecture, but I'm going to take a break and come back, and I will see everybody next time.